Thank you very much. It's always a great pleasure to be here, and so thank you for the very nice words, of course. It is my pleasure to open. I guess it's a bit of a challenge to open with an engineer, more technical than perhaps you would expect. But I would like to discuss today how form and structure also plays a role in what we do in engineering in terms of modeling, maintaining our structures and infrastructures. And to do this at ETH Zurich, we are, in my group, we're about 25 engineers and scientists of diverse backgrounds. We're in the, let's say, in the border of different disciplines. So we have electrical, mechanical, and of course civil engineers in the group, and material scientists that are working towards this approach for maintaining and assessing the condition of our built environment. And now when I say the built environment, I think for many, maybe not for you, there is this impression that we're discussing large-scale structures, usually often referred to, even referred to as megastructures, that are in fact somewhat static and immovable objects. But in reality, this is not, this couldn't be further away from the truth. Actually, our built environment is like a living, breathing organism. It is exposed to the elements, to the environment, the variation of the climate. It is aging, and it is, of course, in dire need of our attention and of ways in which we can take care of it. And to do this in our group, we are treating the constructed objects, structures, and infrastructures such as bridges, energy structures such as wind turbines, the houses that you live in, as cyber-physical systems. And we're able to do this today because today, more so than ever, we have the possibility to use sensor technology in different forms to gather various types of information from these systems, whether it is their motion, which exists, whether it is their straining, but also the actions of the environment. And we also have the opportunity to build digital twins, digital replicas of these systems that can then allow us to best treat them and manage them in the long term. And we do this by using the so-called practice of structural health monitoring, sometimes abbreviated as SHM, which starts from the collection of data, which comes, as I mentioned, in diverse and heterogeneous forms, but of course is just raw information that has to be interpreted by means of suitable indicators so that we can actually extract information that can help us diagnose and prognose these systems. Diagnosis has to do with the understanding of the condition of the system as is currently, right now, and prognosis is the forecasting of how it will perform under new loads, under additional loads in the future. Now, in our group, the particular way in which we, what we practice for deriving useful information from these systems is physics, and we actually use physics as a type of structure that we impose to our formulations in order to be able to reflect upon these systems, and not just individually as individual objects, but really as systems that have to do with the collection of objects that could be the structures of our transportation network, of our energy systems, and so forth. So here is a bit of our activities, because we don't just work with theory, but we also actually work with the data, and sometimes we produce this data that we collect. We produce data from movable objects, so by using sensors on railway infrastructure and sensors on trains, we can actually assess the condition of the traversed infrastructure and the trains themselves. This is the so-called mobile sensing. We, in fact, own a wind turbine not too far from our campus. It's actually in Winterthur, but we use it as a living lab where we practice different technologies for the sensing of these systems and let's say also their optimal repair and management. We, of course, monitor what you would call traditional civil infrastructure, which has to do with buildings and bridges, but also mechanical systems that are themselves event structures. Now, there's many ways in which you can use sensors, and the most typical ones are electromechanical sensors, which are not too different from what you have in your iPhone, but lately we have been experimenting also with living sensors, and so we have been using mycelium, which is one of the things that you would see installed here in the room, but we have been using it not really for building. We use it on the premise of it being recently a construction material, but in fact, we use it as a sensor. It turns out mycelium has electrical properties that allow us to use it as a sensor, which can react to different kinds of stimuli, different types of straining, changes in its environment, like exposure to, let's say, chlorides and so forth. And so we're trying to use its intrinsic properties as an alternate type of sensor that you can imagine already existing in conjunction with structural materials and even instigating special properties such as healing. Now, in this kind of understanding, I would like to here claim and present the way in which form makes a difference for us. And the very first thing you can imagine about form is, in fact, the very nature of the structural response itself. And I mentioned before that structures are living and breathing organisms, and it turns out that you can, in fact, hear the response. So I have here the translation of some of the signals that we measure into sound, and you can also see them plotted in terms of time, but also frequency, which is in a way the different tones that are making up the sound of the response of this system. So this is what you would get from sensors installed on a train. You can hear the effect of going over different slippers. This is what you would get from a wind turbine. It's annoying. And this is what you would get from a bridge, which is a bit more smooth, let's say, but still indicative of the way in which it performs and how it reacts with the loads, including the loads of traversing traffic. So we know that we can view signals and we can hear them. And if you pay attention, you will see that there are patterns in those kinds of signals that are being assembled. In fact, these patterns can be decomposed in what we call the different modes of how the system responds. For example, for a bridge, if I was to take the previous sound and break it down to components, then each of these components would be translated into a different fundamental mode in which the bridge can deform. So you see here, each of these ways in which the structure deforms are actually can be composed to give you the total response of the bridge. For us, this is important because by decomposing this response, essentially breaking down into different tones or acoustics, we can also understand the ways in which these bridges are susceptible to different kinds of hazards, such as, for example, earthquake loads that target specific parts of these so-called modes. And if you were to translate each one of these into a sound, they would be a different clear tone, something like this, which would correspond essentially to a sinusoidal pattern. So by looking into these modes and understanding how the system is affected by its loads, we're able to interfere and we're able to affect even the design of these systems. So I'm going to show you here such a principle where you can exploit pattern and forms that have to do with vibration, the way in which structures deform, for improving their behavior. One such approach are the so-called metamaterials, and metamaterials are very special periodic constructs that have exotic capabilities. You here see such a material which has a controlled mechanism that is a rather strange way of deforming under compressional load. You see here a specific metamaterial that has been used to fashion a door handle, which allows you under mechanical stressing to get different types of deformation that are counterintuitive to what you would expect from a common material. These materials have been used also with electromagnetic phenomena to create different types of optical effects. This is an optical illusion, for example, that you can create by using these kinds of patterns, and they also influence sound by interacting with the acoustic waves. So one thing that you can do with these periodic structures is to influence how they affect the propagation of sound. So this is what a solid material would sound like. It would actually transfer the sound from the source. And this metamaterial, where you see these periodic patterns, is actually acting like a filter. So it is, in fact, a proper insulation material, which is almost as good as air. What we have been doing in our group, we have been exploiting this principle to protect structures from earthquakes and seismic waves, or even vibrations of different types of sources, such as, for example, trains that are creating, of course, in their passing also some sort of vibration. And we're trying to minimize this by protecting the structures through barriers that have this specific periodic form, which you see here. And you see how the wave that propagates from a source is actually deflected merely by the presence of such structural forms that have a specific periodicity. They're placed at specific distances, but also a specific pattern that helps this phenomenon. We have been exploiting this in two ways to protect, first of all, assemblies of structures. You see this here in a sort of scale by using barriers of resonators that are placed in periodic patterns. And we have constructed different types of experiments to show that indeed by using appropriate periodic structures that can vibrate or resonate, you can create a protection barrier around the targeted area of interest. But we have also been building different types of devices that you can imagine as new types of foundations for buildings, for example. So here you see the concept of these meta foundations that are actually, again, periodic structures that you can place at the bottom of the columns that are supporting your system, your building in this case, and in the event of an incoming wave, excuse me. Yeah, let me see if we can start it. So in the event of an incoming wave, the idea would be that you can again protect the system in a much more efficient way than by using plain foundation. And all of this is because of the form, because of the structure of the periodicity that is inserted into the system. Now, form is not only helping us in design, but it's also helping us in assessing structures, which is a primary goal in our group, condition assessment. And the way in which we try to do this is by looking for patterns inside the data that we collect by using these various sensors. Here I'm showing you an example from wind energy infrastructures and wind farms in particular, where you see that there exist interactions between the components, the different farms within the different wind turbines within the wind farm because of the way in which the flow of the wind is being distributed and because of the placement of these different machines, which is actually causing also different types of loads and different types of engineering strain that is experienced by these systems. By using this data and by using appropriate artificial intelligence techniques that also is part of the AAA experiment talks, we're actually able to decipher and reproduce the patterns of this wind flow, which we use to our benefit. We use them to try and recognize not only the flow of wind as it takes place over time, but also the way in which this is translated into an engineering strain, a quantity that can be used by the engineers to understand the current condition of the system, but even design it in a better way to anticipate elevated loading in the future. There are a few more things that we can do by looking into these patterns, and the first of these is to extract robust diagnostic indicators. So by assembling our data that have to do with the response of the system, which already we argued is a dynamic response, it's a vibration, that if you were to plot it in time and, let's say, tonal components, frequency, it would look a bit like this. So you already see specific patterns here that are obvious into this kind of response. You actually see how the response oscillates in different modes, as we say. These are the different ways in which the wind turbine deforms. So we collect this information and we further condition it on the changing environmental and operational conditions that also affect the response of these systems over a greater period of time. So these are acting agents that also need to be accounted for. And without going into the details, we have a series of tools that we have been developing in our group to take care of this kind of dependence, which at the end of the day help us produce a model that reproduces the response of the system. And if you're able to do this, then it means that you can also check whether what you produce and predict is different to what you're actually measuring. And this is a very useful quantity for extracting indicators of damage to the system. So by looking at this deviation, something that would look like this, you collect this over time, and of course, you would have instances of this deviation or discrepancy that are occurring, which are called outliers, and which are not necessarily always persistent. So it's our job as engineers to take a step further and understand these outliers, look into these patterns in a statistical sense, and figure out whether they are persistent, whether they are appearing within intervals where we would expect them, whether the response that we collect is appearing within thresholds that we would expect is describing a normal operation, so everything is okay, whether we're picking up outliers in areas where we're confident that our model can predict well, and therefore this means that there's something going wrong with the system, which is when we would issue a red alarm. And there are, of course, also instances where we pick up outliers, so anomalous behavior, but where we're not confident about our prediction because maybe there's a new range of wind that is acting on our turbine, a higher type of traffic load that is acting on our bridge, and there we issue this kind of orange alarm. And we use this kind of labeling as a way to interact also with the engineers and understand, give them some sort of understanding on how to intervene if needed onto their system. However, of course, this is not enough. Just signaling whether there is an anomaly is never enough. This is what is the task of diagnosis. What we would like to do is go a step further and understand ways to predict the future, predict the performance of the system. And so the moment you want to go away from the task of diagnosis, which is excellently taken care of, at least to some degree, from data-driven methods, so the moment you wish to go to the task of prognosis, you have to bring physics into the loop. So this is our additional element of structure here. It is our intuition as engineers to interpret what it is we gather and what it is we observe through the prism of physics. So the merger of data and physics-based representations that are usually our engineering models is what we would call hybrid models, and what you may have heard of today as digital twins. It's nothing other than the synergy of these two that give you the potential to continuously track a system as the data is obtained, but to also be able to render its response in areas beyond those that are being measured. We call these constructs that we deliver hybrid real-time digital twins. Real-time because we try to deliver, in our case, representations that can compute as fast as the data is attained so that you can take very quick decisions. For example, what to do in a building that is exposed to earthquake. When you gather information from sensors, you can have early warning systems that, if your computing system is fast enough, could point out what to do next. Or if you wish to optimize the control of your system, which is maybe an aerospace structure or wind turbine, you need to have models that can compute the dynamic response in fragments of a second, which is a large part of what we're trying to do. And we do this under various challenges, varying environmental and operational loads, distributed loads that are not easy to quantify, and of course for systems that are highly complex. I show you here such an example from a collaboration with Siemens Industry Software as part of a European project. This is work of one of our PhD students, where she gathered information by means of sensors from this kind of wind turbine blade inside the lab. You see it being tested, and she essentially coupled this idea of a model of the system, an engineering model of the system, in this case a finite element model for those who may have heard of this, together with the data that we receive from the sensors, that is acceleration and strain information. And she does this in a way that does the fusion very, very fast enough to deliver the visualization of the system in real time to the engineers in the form of this tablet application, where you see not only the information that is being measured by point-wise, a few point sensors, but actually in the full scale of the monitored system. Now, if we have this information, then we can do a lot more with it. We can diagnose the condition of the system, but also build indicators that reflect the resilience, the robustness of the system, the reliability in the design, and so forth. One more thing that we have been really working on more intensively in the last years is how to make this more efficient for complex systems. This means systems that may be indicating what we call nonlinearities, or in other words, non-conventional behavior in their response. And in this case, it's not enough to claim that you can adequately know the physics of the system. So in this case, it's not enough to say that you can rely on the physics and the data. You actually have to learn from the data, which is what we call physics-enhanced machine learning in this case. It is the paradigm of using part of the physics that you know, even if it is wrong, and part of a learning representation that can be extracted from the data by the use of machine learning models that are specifically tailored to the purpose of the dynamic systems that we're looking at. It is a type of superposition that is not perfect, but it's actually reflecting a balance which we say exists in a two-dimensional spectrum that gives you the opportunity to select different methods, because these methods come in various flavors, but all that you really need to care about is how much physics is available, how much do you trust your knowledge of the system, perhaps as an engineer, and on this axis, how much data is available. So what does your budget allow and how much information is there for you to derive. Depending on this kind of balance, there are different ways to optimally reflect systems, and again, look for interpretations that make sense in terms of form and structure. I'll show you a very simple example just to make a point, which is a pendulum system here. And the pendulum is nothing else than a system that is basically oscillating around an equilibrium point, but it's actually a nonlinear system. If you ask a black box machine learning algorithm that doesn't know anything about the physics to figure the system out, then this is the kind of plot that it would produce. And in reality, what we're looking for is a very structured plot for this kind of system. A plot that looks like this is basically an attractor that reflects how the angle and the velocity of the angle should actually evolve in the system. And the way in which we actually could recover this desired form is by fusing some of the physics of this oscillator into the equation while still learning from data. So we're fusing a linear model of the system. We're using observations that are videos, just image frames over time, and we're recovering the physical form that intuitively we know should be there and should be recovered by the prediction model. Of course, this was a very simple example. In reality, we use it for more complex systems. One of these is the mobile sensing application that I mentioned before, where we use sensors on a car or a moving vehicle, and we're trying to assess the condition of the infrastructure, for example, the roughness of the pavement, which is an indication of how good our roads are. And we do this by fusing part of the model of the car and learning the remainder of what we're missing through the gathered data. There's different ways here to achieve this balance, and there is an optimal one, which is also part of our inference problem. We have been implementing these kinds of this logic and these kinds of techniques also in real projects. For example, in India, we have been using these methods with the instrumented vehicles together with partners, RTDT Labs, which is a spin-off from our group, and Kislev. And we have delivered in the project a way to extract the roughness of the road pavements and the condition of the roads and map them over time. And we're not only using instrumented vehicles that are, let's say, high-end vehicles. We even have this principle moved on to simple robots, such as the one that you see here. And we use these robots to traverse bridges, the shoulders of bridges, where usually you would have the pedestrians walking, and gathering vibration information that we can then use to map the condition of the traverse systems, again, more or less using this labeling of red, yellow, and green behavior and mapping this onto the system. And the final thing I want to show is the fact that you can also introduce structure in other ways in the different tasks that we are dealing with. And one of them is to deal with the experts. Of course, we are the researchers, but then there are the stakeholders, the state, and the engineers, and it's very hard to be exchanging information with them when we have a very different vocabulary. They don't necessarily know the details of the methods that we use. And this is why we have been using graph-based methods, which is, again, a type of structured system, in order to map, let's say, the actions, the methods that we have, and how these interact with the different components of very tangible objects, the different assets that they have in their portfolio. You see here such a graphical representation that is a knowledge base and which allows them to understand how the tools we give them can actually interact with their objects and then be put into use for decision support on how to best optimize their management over time. And then finally, to reach the last level, I said we are not only doing this for individual objects, but we're doing this for networks and systems. And of course, if you imagine such networks, for example, wind turbines within a farm that I mentioned before, you have to know that there are interactions in these networks. And these interactions, we can use them to harness more of knowledge by understanding how seemingly similar systems are interacting within a network. For example, here a wind farm. To do this, we use formal structured tools. We use graph neural networks, in other words, graph representations, to interconnect individual objects and then to build a model that can jointly predict them. And we're actually doing very well by doing these prediction models. We're very close to high-end simulation tools simply by using this additional bias that comes from the structure of a graph that is meant to simulate the system. We're not only doing this for wind turbines, you can imagine this for any type of system. For example, the components of a roadway network where you would have a tunnel that then leads into a bridge and eventually leads into the highway. So we have been using these tools for also diagnostic management of what happens in the roadway network that comprises all of these systems in the face of an adverse event. For example, in the face of a flood, or in a cyber attack that targets the operation of the tunnel, for instance. And so this is our vision, putting everything together in what we call augmented digital twins, all of which rely on this concept of structure, the signature of these structural systems as we understand it, and then as we can decipher it from the data, using the physics, and by interacting with the experts who complement our knowledge of the system at large, and then eventually taking this assessment from the individual objects to the extended networks that we have deployed, not only maybe within a region, but also internationally. And I'm very glad to have found within this initiative also others who are curious about this interpretation of structures as living objects. So I'm showing you here a part of the previous presentation here in the Kunsthalle on October 10th, together with Yanniv Oron. He took those tones from the decomposition of the signals that we gave him. Here, the signals of a wind turbine, the one in Winterthur that we're monitoring, and he merged them with other sounds, creating essentially a new composition that you can hear now. So here you see you hear more prominently the sound of the wind turbine. And here is where he merges it. Oops, I was too fast. Where he actually merges this together with additional sounds. So let me try to click it. Creating in the end a sort of concert that is not just your common, let's say, opera, but also elements of the operating and responding structural system, the turbine in this case. Thank you very much for your attention.
So thank you very much. Listening to you is sometimes I think I live in an under complex world, and I thought that maybe Ksenia, would you like to do a summary of what she said? So no, I'm kidding. Thank you very much. I have one question, but maybe first I give the very first question of the evening goes to Thomas.
Of course, the climate is an important parameter to a lot of your research, I assume. Huh? Now, how is climate change changing your work, and what are your predictions? Is it mild, or you have to revise some of your basic assumptions?
So the good thing about our work is that we always operate on the basis of collected data. So we know from the beginning that we have to rely on what the data evidences so that we can take the appropriate conclusions. Climate change is a type of load for us. It's an acting agent which is adversely affecting the condition of these structures and has been more so doing this in the recent years in increased rates, let's say. By collecting data from these systems and understanding how the increase of this rate is adversely affecting them, we can actually improve not only the subsequent designs, but also understand how to best repair systems that are exposed to corrosive agents that are perhaps more adverse. For wind turbines, it's also a huge consideration because we have stronger winds, for example, that are actually operating onto these systems. And what I'm here advocating is that we have to adopt this kind of behavior. We have to be able to extract data from these systems and not rely in the way in which we designed them years ago, which for sure, in that case, that kind of approach would be inadequate because it was designed for another load scenario and it was designed for agents that were very different to what we're witnessing today. And so unless we understand the way our structures operate currently, as is, and not as designed, we will not be able to manage them. So key to this is the collection of data through this practice of monitoring.
Thank you very much for this very interesting, though difficult presentation for a lay person. I'm the president of Awareness in Art, an association here in Zurich who has done, Martina, whoever has done a lot of exhibitions connecting social issues, political issues, art, and then science, and some of your colleagues have joined us. Now, like Thomas, I was looking for how could this have an impact in my my life, or and when I saw this small connection with the digital, and you mentioned even the word cyber attack. Maybe could you a little bit expand on that, how your work could help on that?
Yeah. By the way, I should explain that all of the frameworks I described here are digital, in the sense that we're collecting this data from sensors, which are digital. This is digital information, and we're collecting it in the form of telemetry. So they're being streamed to us, we're processing them often in real time, and we're trying to make a decision, sometimes even on the spot, on how to act on the system. And cyber-physical system is a system where you can do this. It's not a system under cyber attack only, of course. But the problem of cyber attack is highly relevant also for us. So actually, what I'm showing here in the bottom, on the right-hand side, is the exploration of the Madrid roadway network under a possible cyber attack which would attack the functionality of their tunnels. So here we're asked to see what would be the best way to redirect the traffic in the case of such a cyber attack, so that you can maintain the mobility within the city at the best level possible under different scenarios. And the way in which we're able to do this is by treating the city as a graph, looking into the various scenarios that affect the connectivity, and taking cyber attack into account as a load, more or less, again, something that is stressing, a stressor to our system. And of course here, again, we act with the data that comes through telemetry that gives us the evidence of what to change and where on the basis of what is observed. Otherwise, we would be somewhat blind in making these predictions.
Thank you.
I imagine you're also especially interested in like very non-linear behavior, as you also mentioned. When you work with data, I guess that is just going to be like very sparse, since you have very few of these events.
Yeah.
And then like, how can you deal with that you want to predict something that you're basically never going to see in the data?
This is our biggest problem, and the reason why I insist that physics is the only way out. Okay, so this is the issue with structures that are big and unique systems. In Switzerland, almost all the bridges are unique. And if you expect to just learn from the data in the case of adverse events, it means you would have to wait for many adverse events to happen and a lot of catastrophes before you can actually plan a strategy. So to amend for this kind of a challenge, which is the sparse data, we can complement the predictions of the system by using our engineering knowledge, which should not go to waste, actually, by using engineering predictive models, basically the physics that governs the response of these systems under different types of loads. And in this way, we're somehow augmenting our data set. Okay? And we're doing it, though, in a way that is compliant also with the part of data that we observe. Because if you were to do this only in simulation, again, it would be something completely off. You have to build models and representations that are reflective of the current data, but can extrapolate to the future, essentially. And that's how then you can build these maintenance strategies. You can somehow build decision support for future horizons, which for the case of infrastructure objects can be very large, can be up to 50 or more years.
And does it also transfer across domains?
Well, it depends what you mean domain. So we have shown, for example, transfer from simulated data to real data, which we do often with wind farms. We have shown transfer from one class of monitored bridge objects to others. Another type, for example, you can go from truss bridges and train a model there to arched bridges or monolith structures that are very, very, very different in nature, but are still somehow governed by similar principles if you decompose them, let's say, into an essential representation. There are colleagues of mine who have been experimenting with transfer, also probably what you would call a domain. For example, training a predictive model on aircraft data and trying to predict bridges. Maybe this is what you had in mind. And this is also something we're toying with at a very, very early stage at the moment. But again, there the principle is to use these kinds of structured representations, essentially, again, graphs, that can capture the essential ways in which different components that could be damaged, for example, are interacting. And then you can transfer this kind of experience also possibly to different domains, but you have to be careful there. There's only a limit up to which this can be done in a way that is controllable. And we should also be aware of these limitations and the amount of confidence that we can attribute to our predictions.
So maybe just to finish, the one very simple example I thought was interesting, and I thought about it when you talked about it when we first met. You were talking how you could sensor with monitoring a floor that eventually you could in a home use it, or for elderly people you could predict that. So you measure the vibration of the floor. If someone falls down, you could say the person in room 6 fell down, we should go up there. But then I was thinking about, so you get this data, but what if the person just moved the chair or the bed? How can you make a difference between the body falling down and the bed that has been moved?
Precisely. Actually, the principle by which we can understand and measure that is this kind of propagation of waves. That's why we are actually able to understand, what is going on. Maybe you're sitting right there and you do some sort of motion. I could feel that motion even if I had the sensor here, provided it's sensitive enough, because your motion generates a wave into the solid medium that you're in touch with. And so that's how we can do this indirect monitoring. In fact, the principle is the same with the vehicles. It's an indirect sensor over the solid that is being traversed. And what happens is, if we have sufficient data, we can actually label them to understand whether it is you that is moving or it's a chair that is being actually traversed. Why? Because the signature that is being produced from that recorded signal, which is a bit like the different or essential motions of this bridge that I was showing, it will be different. It will be different for when you walk slowly. It will be different from when you fall, different when you run, and different when another solid object is being scratched on the surface, for example. And all of this is because of this kind of decomposition of the signal that we acquire, that we collect.
Thank you very much. Please, one more applause for Eleni.
Thank you.